Welcome back, physics. At this point, you should have completed the Intro to Waves lab. Either you completed that by using a Slinky, or you did it using the PhET simulation. It's HTML5 compared to the Java file, so it should be working. If it didn't work, I would find a Slinky. You can try to do it in person. A rope would work well, it just doesn't work nearly as well as a Slinky does. There's a lot more dampening in a rope than in a Slinky. But based on that lab, we now want to know specifically what is a wave. How would we define it? So the first thing is that definition, right? A wave is a disturbance through medium from one location to another. So here we have a big wave in water, right? There is this disturbance. It's not flat. The water is really, really disturbed, which is why it's white water here. So if we have a medium, right, now we need to have another definition. What is a medium? And that is a material that carries the wave. So this lets us know the wave is not the medium. It is not the material. So the wave here is not water, but is traveling through the water from the center of the ocean to the shore, something like that. So mediums, we need a little bit more here, right? What kind of materials are going to carry a wave? So mediums allow for something to move through it. So a road is a medium for travel, right? We're going to travel across a road. The road doesn't cause us to travel, but it allows us to travel across it. Another one is the news media is not the news itself, right? The platform of CNN or Fox News or what have you, they are not the news. What they're talking about, what they present to you, that is the news. So they are not the news itself, but the news moves through that platform, right? Yep. Okay. So the same goes for the Slinky or your rope in the simulation. The Slinky is the medium, not the wave. The wave is going to move through the Slinky. And something you should notice is that anything that I have underlined, those are going to be the blanks in your notes for this lecture. All right, so we're moving along here. So when the Slinky is at rest, all parts of that Slinky are equally spaced apart, right? When the tension in the Slinky is equal in all parts, then all separation of the coils are going to be about the same. If you actually use the Slinky and you pulled it out, right, then the spacing of the coils got farther apart, but all of the spacings were even, right? If you have the string or the rope in the simulation, you'll notice that all of the dots are equally spaced apart. Okay, so the parts of the Slinky may displace. They might move up and down or back and right, but they're always going to return to this resting position because forces are acting on it in different directions, and we'll bring it back there. I'm going to describe that in a little more detail later in the lecture here. So the disturbance is the wave. The Slinky is not the wave. Okay, the disturbance is the wave, not the rope. Whatever it is that you have, the medium itself is not the wave, but the wave is carried through that substance, that material, the medium. And this is something that you need to make sure that you start separating in your mind, right? We often think that the wave is made of water. Actually, the wave is traveling through the water, and the water is going to move, but the water essentially stays in the same place, and I'm going to show you how this works a little bit later. Some of you might have seen the link I sent you with how a wave actually moves, and we'll see that too. Here I got, right, we have a dog at rest. There's a great disturbance in the force, so there's a wave of the force traveling from Oleron to Obi-Wan Kenobi here. All right, so some different kinds of waves. A pulse is a single disturbance, right? If you whip the Slinky or the rope once, then that is a single disturbance that is called a pulse. It goes from one location to another, right? It's kind of just a slight variation on what a wave is. Multiple periodic pulses make a wave. So this is periodic, means it happens over and over and over again, like the ticking of a clock. Or like our heart. What about the heart? Does it pulse or make a wave, right? We're talking about looking for a pulse, but it's multiple periodic pulses. So that makes it send off a wave. Okay, so this is kind of hard to see. I took this from Physics Classroom, and if I make this any larger, it makes it unreadable. So if we are thinking in terms of the particles, in your notes, it says over here, let's think about this in terms of the particles. As each of the parts of the slinky is disturbed, forces act on each part. So here we have our slinky at rest, right? It can be modeled as a series of particles. We have the red dots here, okay? So when it's displaced, the spring is attached, begins to exert a force on its neighbor, thus displacing its neighbor from the resting position. So if this one is pulled upwards, right, then this one's also got to be pulled up. And this one hasn't yet, but once I let it go, that wave is going to start traveling along the length. So when this starts to come down, because this is a spring, right, it's pulling in both directions. So this one gets pulled down, but this one's going up a little bit more because it was being pulled up on this side. And now this one's pulled up and pulled up and pulled up. And so then we get this shape. And notice this one is back into its original position, but this one's been pulled upwards. And over time, though, right now, this side is pulling down. And so this one's going to come down, and so on and so forth. So because the system is all connected to one another, right, when one particle is up, that means that this particle is being pulled up, and this particle is being pulled down. So this is at its amplitude, it's going to be pulled back down to the resting position, but this one was being pulled upwards, so this one's going to go up. Right, now that this one's up, this one down here is going to be pulled up, and this one's going to be pulled down. And so you can see slowly that we're going to get this movement from the right to the left. I think that's the orientation of the video here. All right, so I've mentioned several times that the wave is not the medium, it's not the water, it's not the rope, it's not the slinky. So what is a wave made out of? And that answer is energy. Energy is what a wave is made out of. So as the wave is moving through this medium, though, it's not going to be losing energy for the most part. In the real world, there's dampening. There's other forces that are causing that energy to be displaced, sent out into different parts. But if you're using the slinky, you should notice that the amplitude of the wave stays about the same, right? The height that the wave stays at is about the same. If you're using the simulation, you should have seen something else. You could have dampened the wave a little bit more. That means that there's more forces involved, spreading out that energy, displacing that energy. But otherwise, it's not going to be losing energy here. It's moving through the medium, and it keeps that same amplitude of the wave. So both of these facts are distinguishing waves from other energy transfers like collisions, right? We can still get a wave in collisions, right? We have the domino effect, so there's a bunch of collisions. We have a single pulse traveling through, but in a single collision, you're not going to get a wave that's going to travel out farther. Okay. So I mentioned as well in the notes, notice how the amplitude of your wave from the Slinky Lab didn't get smaller as it traveled from one end to the other. It did lose some energy when the wave was reflected off of the other side in particular, right? Your hand, if you're holding on to the slinky, is going to absorb some of that energy. So this changes some of the ways that we've thought about energy transfer in the past. Okay, so this concludes essentially what a wave is. So if we put it all together, a wave can be described as a disturbance. Right, so the medium itself has to be disturbed. I am making a sound wave towards the microphone. My vocal cords are causing a disturbance in the air, and the air carries the energy to the microphone. So it's going through the medium of the air. It transports that energy. If there's motion, we're going to be getting what kind of energy? Kinetic. And it's going from one place to another, right? It's going from my mouth to the microphone or out away from me. and it's not going to be transporting matter, right? When I have the slinky and I whip it from one side to the next, right, the piece in my hand goes up and then back down. The slinky doesn't actually travel. It's that energy that travels through the medium. Each individual particle of the medium is temporarily displaced, right? It either goes up and down or it's compressed. And then it returns to that equilibrium position. So this is our in-depth definition of what a wave is. And so that way we know all of the different parts. So I have the simple definition at the beginning, but this one includes everything that we should know. All right. So some different kinds of waves and some different little explanations that can help us understand it. So a longitudinal wave, that's going to be a wave in which the particles in the medium move parallel to the direction of the waves of motion. Right? So this is a compression wave. Air does this. Right? When I speak, the air is getting denser and less dense. Or the slinky, you should have been able to compress. Right? If you pushed on it, the coils got closer together and then separated out, right? They compressed, and that compression moved along the length of the slinky. That's a longitudinal wave. So Newton's third law explains that this is pushing the particles forward and backward as they collide into each other. As this particle comes in and collides with this one, right, it pushes it, and this one also receives a similar force and is pushed backwards. Transverse waves, this is instead of parallel, now it's going to be perpendicular. So a wave in which the particles of the medium move perpendicular to the direction. So that's going to be most of the waves that we think of, particularly waves in water, right? If I create a wave in water, right, the wave is going to travel this way, but it's going to be moving up and down that way, perpendicular to the direction of the wave motion. All right, two other kinds of waves. We have two different kinds of energy that can be transmitted in a wave. One, we have mechanical waves. So in mechanics, we dealt with potential energy and kinetic energy. And so what it's going to be transporting is the kinetic energy of that wave. And that's going to be most of the waves we think about. Sound waves carry kinetic energy, very, very small amounts. Water waves, of course, are carrying kinetic energy. Your slinky, the ropes, those are all traveling with transporting kinetic energy. Electromagnetic waves, on the other hand, are capable of transmitting energy through a vacuum, meaning they don't actually need a medium. They don't need a material to travel through, which is really, really strange and puzzled physicists for a long time. And what they thought originally was that there had to be something. All waves travel through a medium, so what has to happen? Electromagnetic waves, light, needs to travel through one as well. And we're going to call this the ether. Unfortunately, we experience the speed of light, or we see that the speed of light is the same pretty much no matter where we are, no matter how quickly we're moving. And this caused a problem for having a medium for electromagnetic waves. Or for, a medium for electromagnetic waves. And so we eventually abandoned it. So light is the only thing that is a wave. It's carrying, of course, electromagnetic energy, but it doesn't need a medium. We're not going to get into that in this class in all too much detail. Maybe this is something we want to talk on Fridays for free talk, or maybe something in office hours you could be curious about. Feel free to sign up, by the way. I haven't had a lot of people sign up for office hours last week. If you just want to talk or have a question, please feel free to do so. All right, let's keep going. So I want to make sure I'm up to date here. Okay, there are two check-in questions. The one, a transverse wave is transporting energy from east to west. The particles of the medium will move in which direction, right? So if we have a transverse wave, we can go back up to transverse, right? Transverse, they are perpendicular to the direction. So if it's moving east to west, right? If it's going, I guess, if it's traveling horizontally, then the waves have to be perpendicular. The amplitude of the wave has to be perpendicular. So that is going to be both north and south, right? It's going to go up and then down and up and then down. So it's going to be both directions, not just north, not just south. It's got to be both. Okay? All right. Question number 2. A wave is transporting energy from left to right. So the particles of the medium are moving back and forth in a leftward, rightward direction. Right? So the wave is going this way, and the particles of the medium are moving back and forth left to right. So this is known as a longitudinal wave. It's parallel. They're in the same direction, right? From left to right, from left to right. Okay. All right. Next thing we need, oh, sorry, too far, is the anatomy of a wave. And I didn't underline everything here, but these are all the definitions that you need. So 1, you need the wavelength. That is the length of one complete wave cycle. So in your notes, it shows you what a wavelength is. It's got to go there and back, right? If I have a clock and it's going to make a full revolution, we call that the period. That's the time it takes to go all the way around, right? It's got to start here, go to the other side, and then come back. If I have a wave, it's got to start at the top, go down, come back up. It can't just start at the top and go back down. That's only half of a wave. It's got to go all the way. All right? The amplitude is the maximum amount of displacement from the rest position. So if I have a wave that starts here, goes up, goes down, and comes back, right? The middle line is going to be where that part is going to be. I'm just going to post a picture in here because this is going to be helpful for us. I should have had this in here earlier, but whatever. All right, this is going to be helpful. So here's the wavelength, right? From top, goes all the way down, comes back up. Or we could start here at the rest position, go up, go down, and then back to the rest. So it's got to go there, down, and back up. Amplitude is from that rest position. So if you measure the whole thing from peak to trough, then you have measured 2 times the amplitude. We are not trying to measure 2 times the amplitude, we just want the amplitude. So it's only from the rest position, okay? So the center line of the wave is that equilibrium position I've been talking about. There's a couple of different terms you can use for this, crest and trough, right? You could use mountain and valley or hill and valley. There's a couple of different ways, but when it's in the positive area, we call that the max positive displacement. So things like crest, mountain, hill, or trough is going to be the max negative displacement, or we could call them valleys as well. All right, so those are a couple of pieces about waves, the anatomy. The next thing is the period of a wave, and I talked about this just seconds ago, but think back to the beginning of the year when we experimented with those pendulums. So we described the time it takes to make one full swing, right? If I have it out here, it's got to go there and all the way back. The time it takes to do that is what we call the period. So that's the same for the orbit of planets, right? January 1st to 2020 to January 1st, 2021, we have made one full orbit around the sun, and the time it takes to do that is called the period, or 1 full year, right? Both of these systems are oscillating. They go there and back. Anything that's oscillating is going to be going there and back. So if we go, right now we're not, but going to maybe waking up and going back to bed, we're oscillating our wakefulness. But anything that's oscillating is going to have wave-like functions. So they move out and back to the starting point. If we want to find the speed of a wave, we need to know that time it takes to oscillate back and forth. This is known as the period. So there's the definition down there. It has units of seconds per oscillation, or just seconds, right? Oscillation is just a number. There's not really a particular unit to that. It's just the number of times it goes back and forth. So often in periods, we'll say seconds per oscillation, or just seconds. Both work. Frequency of a wave. Frequency is maybe a bit of a strange term for us, but we do use it relatively frequently. You're not going to escape Mr. Z in these videos. I swear to you. So, basic question: how would you respond? How frequently do you look at your phone in a day? I probably look at it, I don't know, let's say 20 times a day, right? I'd say that's actually probably a low ball estimate. 20 times per day. That is the units of frequency. Or how frequently do you come to school in a week? Right now, 0 times per week. So if we were to define frequency in a general sense, we would say that it's the number of complete vibrational cycles of a medium per a given amount of time. So frequency has units that are inverse of period, right? It's oscillations per second. If we go back, right, it was seconds per oscillation. So if I want to find the frequency, and I think that's on the next slide here, yeah, we can just do the inverse. So if I want frequency, all I got to do is 1 over the period. If I want the period, all I have to do is 1 over the frequency. So that way I'm flipping these units back and forth, back and forth. Okay. So frequency is helpful, period is helpful, and we're going to see how those are used in terms of waves in a little bit more detail right now. So velocity of a wave, and this is my last slide for today. So if we know these properties of a wave, we can now put them together to find the speed. If I know the distance that the wave travels, and I know the time it takes to travel from one place to another, I can find its velocity. But maybe I don't know how far it's going to be going, and I don't know the time it takes to get where it's going to be going. Instead, what I can do is I can use these two things. I can use frequency, and then the other thing that has a length is the wavelength. So I can either do frequency times lambda, which is the wavelength. That's the symbol for wavelength. It's a Greek symbol. Right? If it's frequency, it's oscillations per second, so seconds down below, and then with lambda, we have a distance on top, meters per second. Or we can do wavelength divided by period. So this is your one big equation, or not big, but it's your one main equation that we'll be using for this unit right now. Okay. So I think that is everything. There's a little bit, let's see where each of these parts fit on the wave diagram. So please fill out the diagram of the wave. Just to give yourself a little bit of practice, you can check and see if you've put everything in the right spot. Okay. Besides that, we are done with this lecture today. I will see you guys next time.